Okay, welcome to class. I hope the homework was okay and doable. Only 92 people watched the video on Weibull. There's definitely more than 92 people in the class still, so I don't know how you did that. I hope if you're one of those people that didn't and you struggle in the Weibull question that you will get help, because that's not going away. There will definitely be at least one question on that on the midterm 3, and I usually put it on the final too. So that's something that's not going away. You definitely need to learn it, because like I said, I think it's one of the key things that you're going to get out of this class that's most useful. Yeah, Chris? Is it Chris? When is midterm 3 is a great question. Midterm 3 is currently scheduled for next Friday. So not next class period, but the Friday thereafter. That conflicts with a bunch of people who have like multiple exams that day. So I'll never write 2 exams because it's just too hard. It's too hard to make sure that it's fair to everyone who takes it. But one thing I am considering is potentially we could take it the Monday thereafter. I need to talk to my TAs because that means we'd have to find a time to grade it. And it's much easier to grade it on the weekend than to grade it on like a Monday night. So if the TAs aren't terribly opposed, now's the time to write them pleading letters, then potentially we could do it on a Monday. It's not working. It's not great. So by next Friday, I will have an answer on when the exam will be, but plan on it being the Friday thereafter, right? Is it November 11th, I think?
November 11th.
Plan on it being November 11th unless we can have a change of heart. Oh, so if Monday's no better, then yeah, we probably won't. Okay. Okay. So that said, let's get started on today. So today we're actually a little bit behind, which is not a problem. So today we're going to wrap up chapter 8, which I'd hoped to finish before. And there's not a lot left on chapter 8 because the hard part is deformation in metals, because we do the whole single crystal thing. And that was useful, and it's good that we spent the time yesterday in class working that out because I want it to stick. But today we do need to talk about deformation in ceramics, and then we need to talk about deformation in polymers. And there's a couple key points to cover there. And then I hope we have time to actually start chapter 6, which is diffusion. So our learning objectives are talk about mechanisms for deformation in ceramics, polymers, glasses, basically everything else other than the single crystals we've talked about thus far. We'll talk about viscosity a little bit more and why it's useful for talking about deformation. And then finally, we'll relate things like molecular weight, crystallinity to deformation in polymers and the heat treatment of polymers. So ceramics. Ceramics, we know that they don't deform very much. This piece of chalk, this is a ceramic, right? I can try and bend this, but it's not going to deform, right? I'm bending, and it just breaks, right? Because it has no what? This is a good question. What does it lack that other materials have, why it does not bend? So a common response based on what we talked about already, it's like, well, it has no twinning possible, or it has no slip dislocation, like slip systems, right? So that's kind of the answer, but it's more complicated than that. It really comes down to the fact that you have anions and cations. So take a look in our system here, right? Dislocation and slip it's uncommon not because you don't have highly packed planes. You can have highly packed planes and highly packed directions, but the problem is, think what happens when you try and slide this thing past, right? So pick a plane, right, like in the drawing, a plane like that. If that happens to be our slip system, and let's say it's slipping this way, what will happen as you slide this half of, a bond length over, now all of a sudden this negative is going to be next to another negative, and this positive will be next to another positive, right? And that leads to really strong Coulombic, basically repulsion, right? So it has to overcome a very high energy to slide past one another. And then when it slides to its full position over, like by the time that this negative anion has gotten to that point, then it's back to normal. But it's getting there that you have to overcome a prohibitively high activation energy, right? It's just not likely. You have to have a ton of thermal energy for that thing to slide past it without it just saying, you know what? It's cheaper in terms of energy for me to just break. And so oftentimes, if you're at low temperatures like that chalk just was, I'm bending it, and instead of twinning or slip dislocations starting to move, it just says, I'm just going to break. It's just not worthwhile for me to try and get that close to ions of the same charge, right? So it doesn't happen. It has to do with electrostatic repulsion as they slide past one another. Since metals are electrically neutral, you don't have that problem. Covalent ceramics, Slip is also uncommon, but here it's not because of electrostatic repulsion, it's because covalent bonds are so strong, right? To break that covalent bond, imagine diamond, right? Diamond is a bunch of carbon bonded to carbon in a three-dimensional lattice. If you want to make that thing slip, you have to make carbon break a carbon bond, right? That releases a lot of energy. At that point, it's more common for it to just fracture, right? And they often do have complex structures because covalent bonding is directional. It leads to complex structures, which oftentimes means you don't have these nice, really high-density planes, really nice high-density directions to slip on. Okay, what about glasses, non-crystalline ceramics? Question? No? Okay. So deformation is still not likely in glasses, which are non-crystalline ceramics, but now it's because you don't have a regular atomic structure. You don't have a really nice plane. Like in this row of students here, right? We said that I could have slip. I could take this couple rows here and slide them that way, and it's not a problem. But in the glass, you don't have nice regular rows. It's just a hodgepodge jumble of atoms that are sort of frozen in place, right? And so you don't have slip systems, essentially, okay? Instead, how do we get deformation? You get it via viscous flow. Glass, if you heat glass up, all of a sudden it becomes something that can flow really easily, right? So my students that did a glass lab did that recently. They actually made their own glass. They got it good and hot. They got all the bubbles out, and then they cast it onto these hot plates, and they literally poured it like you pour honey. It doesn't flow like water unless you get it super hot, but you know, it flows. You can actually flow it. So this rate of deformation is going to be proportional, for one thing, to the applied stress. If you're pouring it, that's just gravity, right? Gravity's pulling on it. But you could also put this in like an injection molder. You could apply a stress, right? And they do that. And it's going to be proportional to that as well as the viscosity. What's viscosity? You would have heard this term before if you've taken transport. Viscosity is a measure of how sort of thick a liquid is, right? And at some point, a liquid goes from something really thin like water, or water with soap in it, right? That's really thin, to really thick like honey, or even thicker to like honey that's cold, right? So that transformation from something that flows to something that doesn't flow as a fluid, we use viscosity to describe it. Literally how it's measured is you take a moving plate, you drag it at some velocity. Let's say this is like the surface of my liquid I'm testing. I drag it, and I know the velocity of the plate that I'm dragging. But that velocity gradient occurs between the top plate and the bottom plate, right? So I had two plates, I'm moving the top one. The liquid that's touching the bottom plate's not moving. The one at the top is moving. So this gradient in velocity of the liquid that's moving, that basically is proportional to your viscosity, right? Your viscosity is equal to the shear stress you apply divided by this gradient in velocity. Any questions on that? Sometimes that's hard to, I think, grasp for students. We're not going to say more about this or how it's measured in this class. When you take transport, mechanicals and materials, we'll have to take that. You'll learn way more about it, so I'm not going to say more. Last chapter, we mentioned that the Glassy transition temperature is a temperature defined at the temperature at which your viscosity is equal to 10 to the 12th Pascal seconds. That was in last chapter. I double-checked the notes. We're just confirming that again here, right? That is a totally arbitrary definition, right? Totally arbitrary. They just picked it. They said, at what point does a glass kind of start to move around a little bit? When the viscosity is around 10 to the 12th Pascal seconds, right? Totally arbitrary, but the whole community has accepted that, right? That said, viscosity can be calculated at any temperature using a series of different expressions. In this class, the only one we're going to use is the Wlf equation, wilhelm-landau-ferry, which says the following. The viscosity at any arbitrary temperature is equal to the Glassy transition viscosity, 10 to the 12th Pascal seconds, times exponential of this, negative 17.4, times the temperature that you're at minus the Glassy transition temperature, divided by the quantity of 51.6 plus that temperature minus the Glassy transition, right? So these WLF constants, like this one and this one, those technically are constants for a given material, right? You'd have to look them up for a given material, right? These are general values that work for a lot of things, but if you want to be very specific, you have to know what those constants are for a system. So if you buy motor oil, that might be something that's provided on like the spec sheet or something. What are those constants? So you know, all right, how's the oil in my car going to change when I start it and the oil's thick because it's cold versus when it's running and it's running at whatever temperature, some high temperature, right? And now it's thinner. Okay, let's talk about polymers. So that's really it. You really can't deform ceramics and glasses in other ways than that. Ceramics, if you want them to like have slip dislocation, you got to heat it way up, and I'm talking like really, really high temperatures before you get even nominal deformation. It's not going to be a lot, but it'll be some. And then in glasses, again, you got to heat it up so it can flow. Okay, very different than the slip and the twinning we talked about previous.
So going back to the equation, you said, so is it a negative constant, or is for like the negative 17.4? Is that value negative, or is that
good question? So I've added the negative from the constant in there. That's a good question.
Okay.
Right. So you could use this as is, that equation as it's written. That's a great question. Okay, what about polymers? How do they deform? Different, very differently, right? So we're going to talk about crystalline versus semi-crystalline. First, let's talk about semi-crystalline polymers. Semi-crystalline polymers, we talked about this a couple chapters ago when we talked about the structure of polymers. There's regions of the polymer that are kind of like this middle section of the row, where you've got like folds of the polymer folding back on itself, and there's bonding between these layers. It's not super strong bonding, it's van der Waals, right? But it's bonding, right? Along the chain, that's where our strong bonding is. But between these things, right, which we called, what do we call them? These were, again, they call them lamella. It's the same word as lamella, we talked about phase diagrams, but a kind of different meaning. But between these sections, you've got a region of something else, and then you've got another section, right? So what happens in here, this is where the chains are just random, right? So you've got blocks of organization separated by sort of randomness, right? In that top left picture is kind of where you can see a diagram of that. So if you pull on this thing, particularly if you pull on a different direction than how these things are oriented, right? So this middle row is oriented like that. So if I grab this polymer and I start pulling it this way at some odd direction, right, like that, what's it going to do? How's it going to respond? Well, it's going to do the easiest thing first. And the easiest thing is to stretch out the amorphous region, right? That amorphous region was already not very well bonded, so stretching and breaking those bonds, there's not many of them to break. So it's going to stretch first, right? So overall, you do get some elongation as you pull it up and down, right, by doing that. If you keep on pulling it, the next thing it's going to do, it doesn't want to break these bonds yet, but it can slip them, right? It's going to rotate it, right? So if I was pulling this whole row of students, the rows would sort of orient towards the direction you're pulling it, right? They're not breaking yet. They just, some energy went into orienting them in a different way, right? Keep on pulling it, and finally this row is going to start to break up. Sections will come forward, sections will go that way, right? It's going to break up a little bit. And you keep on pulling it, you're finally going to get really a dramatic example of going from 4 to 5. It's just more of the same, but more dramatic, right? That's deformation in polymers, right? Very, very different than what we talked about in all the other systems so far. Matt?
So we're kind of like unraveled the solid regions?
Parts of the solid regions actually do get unraveled a little bit, right? These lamella, the ratio of lamella to amorphous would probably shift towards amorphous a little bit. I couldn't say how much, but that's the concept, right? At least conceptually what's going on here. So these are the steps, right? We've talked about them. Spherulites, which is the overall organization. Spherulites were like the blocks of organization separated by amorphous, another block, right? It had like this big region. Those get destroyed in this process, right? We went from something that was more ordered to something that is now stretched out, and we changed the order in it, okay? So, interestingly, when you heat these back up, you restore the spherulites, and the sample is going to shrink back, tending towards the shape it started at. Right? Very different than metals, right? You took a metal and we cold or hot worked it and we achieved deformation, but when you heat that back up, all you do is you either get rid of dislocations via recovery, or at most you do recrystallization and you grow new grains, but the deformation, like this object, is permanent. It stays put. Polymers, it's different, right? When it's in this state, right here, if I heat this up, I'm basically saying, here's some energy, lower your energy. Use that thermal energy to lower your system's energy. And it says, great, I can do that by bringing these together, by closing it up, basically by trying to get back to that state. And so when you heat a polymer up after it's been drawn or something, it's going to shrink back to its original shape. It's going to tend to, right? Because you're giving it thermal energy for it to go from a higher energy strained state back to something there where it wants to be, okay? So that's completely opposite of metals. Okay, because polymers can do this, we already talked about this. We talked about stress relaxation. So I'm just going to remind you again, here's the formula. We'll see it at some point. We saw a variation on the homework this week. We'll see it again. But again, if you load it up to an initial stress naught, so again, that's our initial. That's our initial stress, right? If you know what the modulus of your polymer is, how long it's going to be held there, and the viscosity of your polymer, you can calculate what the stress will relax to after a given time at some temperature, right? So that's our clicker question. Let's start with that today, which says the following. At the Glassy transition temperature, you observe that a stress of 100 megapascals produces 10% strain. Okay? What does this stress decay to after 2 minutes? Give your answer in megapascals rounded to 1 decimal place. And I'll remind you that at the Glassy transition temperature, by definition, this equals 10 to the 12th Pascal seconds. And I'll also remind you that technically things inside of an exponential have to be unitless, so make sure your units cancel or you won't get the right answer on this. Your units have to cancel. Anybody need help getting started?
No, this is in Pascals, but this is our modulus is really just what units we strain is useless.
Okay, another couple minutes. Okay, one more minute, get your answers in. Okay, final answers in. Closing the poll. Okay, we good? Just a second. Yep. What's happening? Why? Why does this pen always break? Okay, gonna close the poll. We good? We're good. Okay, what do people think? Okay, great. Majority of you guys, 3/4 of you get the right answer, 88.7. So how do we get that? Where did it come from? If my pen's gonna work, we can work it out. Why is this not working? Alright guys, bear with me. My pen stopped working. This is the worst thing ever. Alright, now I'm going to type it out. It'll be even easier just to type it. Just call it. Okay, so in this case, E equals the stress over strain, right? Right? That's way too small to read. Let me fix that. Right, so that's equal to 100 megapascals over 0.1, which means our modulus is equal to 1,000 MPa. Right? Okay, so now we've got our modulus. So now we can just plug it directly in this equation. We can say that sigma, our stress, equals whatever our applied stress was, which was 100 megapascals, times exponential of what? It's going to be, let's see. So we've got negative 1,000 megapascals. Let's convert megapascals into pascals so the units cancel. Right, so now it's pascals. And then we need this to be in seconds, so the seconds cancel. 2 minutes is 120 seconds, right? So this will be over 10 to the 12th Pascal seconds, right? When you plug all this in, you get 88.7 megapascals. Megapascals because this has no units and the megapascals carried over, right? Any questions on this? No? Any questions? Okay, let's keep going. Okay, a few more things to say about this. Molecular weight. The modulus is unaffected by molecular weight generally, but the tensile strength increases with molecular weight because molecular weight means it's longer and longer chains. So the likelihood of this chain tangling up with another chain over here and pulling on it and getting stronger, pulling on the covalent bonds, increases. So tensile strength goes up because of basically more entanglement. The degree of crystallinity. If you go from something less crystalline to more crystalline, you're going to change the bonding, right? Secondary bonding is prevalent in the crystalline regions. That's where there's good overlap. So basically, if you increase crystallinity, you increase modulus, and you also increase tensile strength. But it also becomes more brittle, right? Because the amorphous regions are the ones that are able to flex more easily, okay? Pre-deformation by drawing, a common way that we work with polymers, the way that you get like your grocery bags, things that are polymers but really, really thin, they start out with a melt, and they take that, and they, like grocery bags, they make by actually inflating them. It's a pretty interesting process. they inflate it, and as you inflate a balloon, it's going to get thinner and thinner and thinner as you fill it up, right? So that's how they get really nice thin things for a lot of polymers. Or they'll draw it. Like if you want fibers and you want strong, thin fibers, you draw it down. So climbing ropes and that you want really high tensile strength in one direction, they'll take it and they'll draw these fibers, right? As you draw it, you go from, you know, in the molten state, there's going to be kind of like this, and you're going to turn it into this. So what happens to the strength? Well, you lined up a bunch of these chains. Now when you pull on something, you're pulling on the polymers in the chain rather than just stretching the chains out, right? So it's going to be a lot stronger and a lot more likely to, it's going to be less ductile as well, right? So it's just like strain hardening, right? It strengthens them. It produces oriented polymers. These are obviously anisotropic. If you draw a polymer this way, you're going to have a lot of strength in that same direction. And transverse to that, you're going to have a lot less strength, right? And it can be pretty significant. If you, for example, take something that's oriented and then you pull 45 degrees off of that, you could see strength reduction by factors of maybe 2 to 3, right? Pretty huge drop in strength. If you draw it at high temperatures, then you have to quench it to retain those high temperature properties, right? Because thermal energy says this polymer is going to want to shrink back down and go to a nice spherulite. So if you want to maintain these high temperature properties, you've got to quench it, right? You have to cool it down, get rid of that thermal energy quickly so it keeps its high temperature structure. And then, like I said before, if you do perform heat treating, you're going to go back to the spherulites, right? It's going to go back to how it was when it started. And in doing so, you become more ductile and you lose strength, right? Opposite effect of what happens in metals. Deformation of elastomers. Elastomers are a lot like polymers, but now we add something. We say that they're cross-linked. So instead of just van der Waals secondary bonds, which are holding these things together, now you add a few really strong covalent bonds periodically by adding the vulcanization agent, right? Sulfur or something. So you get very similar properties, but it has more to do with chains catching and entangling due to those cross-linking, right? And that is all I'm going to say about that. So let's move on to Chapter 6. Chapter 6 is on diffusion. Okay? So here's our learning objectives. Maybe my pen has decided to work again. It's back! Remarkably. All right? So the learning objectives for this chapter are, let's talk about the needs for diffusion in real engineering problems. Is this just something that, like, all right, scientifically exists or whatever, or is there actually a need to understand this? Yeah, you betcha there is. We'll talk about how atomic motion and the equations that describe them can be used to govern diffusion. And if we have time, we'll talk about activation energy and the potential gradient, chemical potential gradient. I don't know if we'll get much further than that, so let's get started. So where do we use this? We use it all over the place, right? A couple chapters ago, we talked about case hardening, right? We said that if you want to strengthen material, the surface is the best place to start. And they did something called shot peening. What was shot peening again? What was accomplished by shot peening? Matt.
Put a certain part in compression where the other parts.
Yeah. We know that things usually break easier under tension rather than compression. And things start at the surface because the flaw size is half of what it would need to be in the inside due to Griffith's fracture equation we talked about. So shot peening basically deforms the surface like crazy and puts it under compression. Therefore, to break under tension, it has to overcome the compression first, right? So there's another way to do it. Shot peening is one way. Case hardening is another, sometimes called carburizing. And we do this in my own research group, actually. Pull this up. So if we go to Meeks, Shetty, Sparks, tantalum, carbide. We just wrote a paper on this. I think I'll have it be part of the homework due next week. But basically, we started out with a material that wasn't as hard, but it was really tough, right? So we wanted to make this thing both hard and tough. We want the surface to be hard so it can be used as a cutting tool, but a cutting tool does you no good if you go to like cut something and it just fractures, right? So we wanted it to be nice and tough, which the bulk already was, and we needed to introduce carbon from the outside into the material by carburization to make now a functional material, a functionally graded carbide, basically. So you'll learn more about that on the homework this week, I think. But they do this all the time, and they've known about it for a long time. If you have old antique guns, I think they call this patina. It's like the collector's term for when a gun or whatever artifact or antique has that sort of tarnish on it. That tarnish is, the function of diffusion of stuff going in there. It can also be oxidation, right? But in this case, they've intentionally taken a steel and they put more carbon into it. What do we know about carbon? Steel as a function of carbon content. Which one's harder? More carbon, and why? Why did we decide that steel's got harder but less ductile with more and more carbon?
Is carbon interstitial?
Yeah, let's imagine two scenarios. One under equilibrium where the phase diagram reaches whatever the equilibrium is, and then the other where you're just forcing something in and then you freeze it. You don't give it time to reach equilibrium. Under equilibrium conditions, the further you are towards the right where there's more carbon, you're closer and closer to the cementite phase. That is a ceramic. No surprise that it's harder and more ductile, or less ductile, right? On the left, you've got pure iron, right? So that's the first reason, under equilibrium. But this is not necessarily happening under equilibrium. They start out, they put the gun or the artifact or whatever it is in a atmosphere that has lots of carbon, right? They can either coat it with carbon or they use like carbon monoxide or carbon dioxide in the air. And they're driving carbon in. And you don't let it completely equilibrate all the way through the material. Instead, it's just in the surface. So your carbon concentration, right, as a function of depth, x, it might have had like some value before, right? That's like the steel, how it was made. But after you do this, it's going to be higher. It might be something like that, which causes this region to have a higher strength. It's going to be less ductile, but it'll be higher strength because you stuffed carbon in all the additional sites. And what that does, why would that strengthen something? Actually, this is a good question. So you had interstitials, right? So this is our steel, right? I take a bunch of extra carbon atoms, I'm stuffing them in here. Why did I make the material stronger and more scratch resistant? Yeah, because we said for deformation, that's scratching, right? Scratching is deformation. So for me to slide this row of atoms over and achieve deformation, I stuffed extra atoms in there that messed up our slip system, right? It made it harder for these things to slide past each other. It's starting to behave maybe a little bit more like a ceramic where there's more interactions that it didn't like, okay? So that's exactly what happens. You made this thing harder and way less likely to be scratched by stuffing in extra atoms near the surface. Eric?
So in addition to screwing up the slip systems, is it also because the bonds become pre-stressed?
Yeah, this does, absolutely. Another thing it does, not only blocking slip systems, but by adding extra atoms, you're adding compressive strain, right? I'm stuffing too many things in here, it has to do something so it creates compressive strain. So yeah, both of those actually are effective, right? So we've known about this for a long time, but a long time they didn't know the science behind it. Now we can describe how this happens and we can control it, right? So if you want take these, what are these, 6 different materials, right? And if you want just a very thin surface carburization, you can achieve that. See like the 2 different colors here? So you can have thin all the way up to really thick as you control 2 things. 2 things dominate diffusion, time and temperature, right? Those are 2 independent variables you have, right? Another one that we could say technically we have is species, right? Some species will diffuse faster than others, but if there's a certain species you want to use, carbon and steel, for example, you've got time and you've got temperature, is basically what you've got, right? So the question then that we would like to be able to answer as engineers is, all right, how long do I have to hold something? What temperature do I have to take it? And then how thick am I going to get? And when I say thick, like, is it all equal, right? What's my final thing going to look like? Is it going to look like that, right? Or is it going to be a slope? What's it going to look like? How do we predict that? And how do we change that with different processing steps? So before we say more, let's do a demo. I need somebody who feels brave, who's willing to risk life and limb for science. All right, come on up, Steve. You may regret this a little bit. So we have here Axe body spray. So you're going to smell a little bit like an 8th grader. But for science, you're doing it for science. What's going to happen when you smell the 8th grader in the room, I want you to raise your hand, right? You ready for this? Keep smelling. This is my favorite part of the job. Who smells it? All right, Rachel. Yep, the 8th grader spreading. Is this spreading? Oh, that's so strong. Are we probably good? Steve, you're a good man. Thanks for donating your life and limb for science. So, hands up if you smell it. What's happening? You're smelling it first here, and this is sort of like, oh gosh. I walked right through the wave. Right? It's spreading. Now, the way that it's spreading is not technically diffusion. It's something a lot like diffusion, right? This is actually convection, but this is a great analogy to how diffusion works. Diffusion, if you start out with a bunch of carbon, yeah, let's actually open that. Okay. Diffusion, you added a really high concentration somewhere, say carbon atoms, and those carbon atoms have to hop right through the lattice, right? And the more there are, the more it's going to spread that way, right? They're going to go down the concentration gradient, right? So what we really need to come up with is an expression that describes how atoms hop, right? How do atoms hop? What are the key parameters that matter as atoms hop? So let's talk about it. Skip that. We can skip that. We'll come back to that next time. Again, one more time. If you took copper and nickel, like my 2010 students are doing this week in lab, they take actual copper and actual nickel, right? They put them together, and they're heating it up. And after a while, we know that initially the composition gradient looks like this. Like copper goes 100% down to 0, right? But over a while, it's going to flatten out and look something like that, right? Okay. So, this is actually a good graphic of what goes on. Atoms, think of atoms that they're always moving, right? So there they start out with your initial state. They're always moving, and the amount that they're moving is proportional to the thermal energy that you give them. So they're going to sort of pinball around in where their lowest energy sites are, and occasionally they get enough energy to hop, right? But they're going to generally spread out, right? And why? Because think, they're already here. So this guy, he can't hop that way because it was already occupied, but he could hop that way because it was unoccupied, right? So it has to do with atoms hopping and available sites, right? In the beginning, he could not hop up or to the left because those were both occupied, but he could hop to the right or down, and presumably in and out of the page as well, right? So we can introduce some concepts. Grab my notes so I do this right. Okay, as this atom hops from this site to say that site, right? We can draw an energy landscape here. Okay? Now, the initial energy state is low and the final one's low, but when it moves between those two states, it has to break bonds, it has to crowd nearby atoms, so it's actually going to produce a higher energy state temporarily, right? This right here, the distance between these two states, that is going to be our change in free energy during the jump, right? That's our activation energy. For diffusion to happen, it has to overcome the activation energy. So if you have way less thermal, it's so strong smelling still, right? You have to have at least that much thermal energy to get over that, okay? And then the hopping distance, the jump distance, would obviously just be from here to here, okay? So if you have no driving force for jumping, right? We haven't added any driving force, then our plot might look something like this. We've got site number 1, and we've got site number 2, and they are both initially at the same energy, right? You have to go over some activation energy, and so what you're going to have is you're going to have a flux of atoms leaving site 1 to go to site 2 as a function of time, dn1 dt. But you're also going to have a flux of atoms leaving site 2, dn2 dt, right? And if there's no driving force, if we haven't done anything to drive this thing and make it happen, then the flux of those two atoms going one way or the other is equal, right? Just as many atoms hop from site 1 to site 2 as hop from site 2 back to site 1, right? Okay? And again, this is still our activation energy. Okay?
So what does the x-axis represent?
Distance. Yeah, so this is energy, and this is distance. Like somewhere in the crystal. Like, so if we said Rachel's seat to Ryan's seat, right? That's like literally like a spatial separation of those. And when somebody hops from one site to another, there's an activation energy, right? Now, we said that it's got to be unoccupied. So for Jimmy to diffuse, he can't diffuse this way by sitting on Ryan's seat because that seat's occupied. So if he wants to move that way, he has to step like on Ryan's feet over here, right? That's uncomfortable, right? So it's possible, but it has an energy barrier, right? But if he goes this way, there's a nice empty seat. So diffusion that way would be desirable. We'll talk about that, where that comes in here in just a minute. Yeah, Eric?
So if you're thinking of site 1 and 2 as specific points, how can they both be moving at the same time? This one wouldn't move that way because there's already one there, and so...
I see what you're saying. We're going to imagine two scenarios. In one scenario, like there's equal chemical potential both ways, right? In one case, this is empty and that's occupied. Your flux would be whatever it would be related to your activation energy. And now imagine another scenario where this one's empty and this one's occupied. It'd be the same flux. Basically, all things equal, an atom doesn't care if it goes left or right. That's what we're saying. Unless we bias it in some way and change the energy, which we're going to do in just a second. Right? Everyone follow this? Any questions? We good? Okay. Let's keep going. So we can say that the flux of atoms leaving site 1 or leaving site 2, they're going to be equal. And they're going to equal Vf times the exponential of an activation energy divided by a thermal energy, right? So what is V and F? V is our attempt frequency. Literally, an atom vibrates, right? So the frequency of vibration. Every time that it goes whatever which way it's going, it's potentially making a jump. Like Jimmy's shifting, right? At maybe like 1 shift per second or whatever it is, right? And that's his frequency, right? It doesn't mean that it's a big shift, but he's shifting, right? And then F is the fraction of atoms in the correct configuration. For Jimmy, for him to move from seat to seat, the fraction of atoms looks pretty good. He's got nothing up front, so we'll ignore that. He could go backwards because there's an empty seat. He could go to my left because that's an empty seat, but he could not go right. So it would be 2 out of 3 would be his fraction, right? But other people, like say, I'm totally drawing one thing in. That's embarrassing. Polaroid shirt, totally forgot. What is it? Matthew, I'm sorry. Matthew can't shift at all, right? His fraction is 0, unless he goes into an interstitial site. But we're just talking about on sites for right now, okay? This makes sense? So it has to do with not only how often you're shifting, but what's the fraction of sites around you. And then, obviously, how much thermal energy you have. So because the energy required to actually make a move over, he has to shift from here, clear that much, right? So that's going to be proportional to how much thermal energy he has. If you only have this much thermal energy, you don't move. You don't get diffusion, right? So now let's add a chemical potential gradient to add a driving force for diffusion. Do you have a question, Matt?
Yeah, so F is basically the fraction of how many places they can move to.
Yes. And like I said, you won't be tested on these derivations we're doing right here. When you go and take your thermal class, you're going to learn a lot more about it in detail. I'm just laying the groundwork for the equation is all. So you don't need to follow these details super close. Ben?
I maybe missed it. Just what the K sub B is.
Oh, yeah, great question. K sub B is Boltzmann constant, and T is temperature. So the Boltzmann constant times temperature will give you units of energy. So when we write RT or KBT, we're in both cases talking about thermal energy, but one of them, KBT, is thermal energy per atom, and the other one, RT, is thermal energy per mole of substance. Since in diffusion we're talking about individual atoms moving, it makes sense to use the thermal energy for an individual atom, KBT. Great question though. Okay, so now if we add a chemical potential gradient driving force, we can bias our flux, right? So we're going to change our picture here. Now, let's say our starting energy is up here, but our ending energy is down here, right? We're still going to have an activation energy. Let's say it's still roughly the same. Oh, gosh. Right, so you still got something like that. But now imagine that your flux, let me pick the same colors as before. So gray. Oh gosh. Right, our flux this way, this is dN1 dt. And then our flux the other way, dN2, that's brown. Right, so dN1 is going to be far greater than dN2. And think of it this way. dN1, it still has a relatively small activation energy, at least comparable to what it was before, right? But now if you're going this way, your activation energy like doubled, right? And that's a double inside of an exponential function, right? We said it's right here. This is where your activation energy is, right? So if you double the activation energy, you dramatically reduce the flux going from 2 back to 1, right? Any questions on this? Any questions? Nothing, Ben?
So, like with the first one, you had just 1 activation energy. With this one, you have 2 separate.
Yeah, let me draw it out. So let's draw it. We'll say that this distance right here in terms of energy, that's still going to be our delta GM, right? But meanwhile, on the other side, we have, let's draw this one. This difference in energy, we're going to write that as the change in the chemical potential. Chemical potential, I'll remind you what that was in just a moment. That will be equal to this, our gradient in chemical potential times the separation between the two sites, right? What was chemical potential again? Chemical potential, by definition, if we went back to chapter 10, we'd see it is, by definition, the change in energy of a system as you add or remove a component of a certain type, right? So you guys are all different types of atoms. If I remove one atom of Jimmy from this body of students here, what happens to the energy? Does it go up or down, right? If I add another Jimmy here, right, what happens to the energy of that body, right? That's the chemical potential, right? So now imagine the scenario that we started with. We sprayed good Steve up here with the axe. So the concentration of atoms here, super, super high. So that has a different chemical potential than students in the back of the room that don't have any of the axe body spray, right? So there is, in fact, a gradient in chemical potential going from here to the back of the room, right? More or less linear, kind of radial, I guess it would go. Since it came from a point, I guess it would be radial, right? But there's a gradient in our chemical potential, right? Because of that, you get like this, like, so it may be linear, it may not be linear, depending on how your concentration looks, right? But you get a difference in chemical potential. That's what matters. Therefore, you get higher on one side than the other. Okay? Any questions? Yeah, Teek?
Can you explain more what dN1 dt represents?
Yeah, so great question. N is the number of atoms at site 1. So N1 is number of atoms at site 1. T is time, right? So dN1, that's the derivative of the number of atoms at site 1 with respect to time. So it's the change. It's the change in atoms as a function of time. Like in 1 second, how many atoms leave site 1? 1, 10, 100, right? Depends on like the rate at which they're leaving, right? Obviously the rate at which they're coming into it again too, right? Kylie?
So that's saying, because there can only be one atom inside one at a time, right? So that's saying like basically how fast they're cycling through side one?
That's one, yeah, that's one way to think of it actually, right? Obviously if you keep on moving atoms out of it, they'd have to keep on coming from somewhere, right? But yeah.
So then with your driving force,
Okay.
can you explain again the difference between like if dN1 or dN2 is lower?
Okay, so all we've done is by adding a chemical potential gradient, meaning there's a difference in concentration, that will produce a chemical potential gradient, we make one energy state lower than the other. And maybe the way to think of it is like, imagine I had like a bunch of extra people, and I'm like, hey, we got to put them in this row somewhere. And I say, all of you extra 20 people sit in these front couple rows, right? They're going to like cram in here, right? Which makes this front couple of rows uncomfortable, energetically unfavorable, right? So those extra rows of people are going to like slowly, awkwardly like try and like shift further back, right? Because it's lower energy. There's less stress. There's empty seats further back, right? That's exactly what's happening. You have higher energy here because I crammed extra atoms here. The concentration was higher. Concentration, right? And there's lower concentration in the back of students, so they're going to work their way backwards because it's lowering their energy. Atoms are doing the exact same thing. If we go back to that Wikipedia image, right? They started out, we had a high concentration, right? But there's empty seats that way, so they're going to slowly diffuse down the concentration gradient because that's moving down the chemical potential, and it has to do with flux, right? Some of these atoms will hop back. I hope in the graphic they include at least one hopping back, but the overall rate should be mostly spreading that way. Yeah, in the back?
And then there will be a time at which like dN1 dt and dN2 dt are equal, like an equilibrium point, where like...
Exactly. That's a perfect question. Like, when will diffusion stop? When the chemical potential doesn't exist anymore, right? So if I add these 20 extra students and I say, take a seat, but I have them start here, they're going to move their way backwards. Once they're sort of evenly distributed, students stop moving around, right? Atoms are just like people, right? They're going to quit moving around because they're sort of even, right? That means that the concentration is more or less equal. Once you have an equal concentration throughout your material, there's no longer a driving force for diffusion. Does that mean that all movement stops? No way. It means that the flux going forwards, or backwards to the back of the room versus forwards is equal. There's just as many students going backwards as there are forwards. So there's no net flux. It's just random, hopping around is all. Any questions on this? Good questions today. We're out of time, so let's pick up here next time.
Thank you.